What specific problem does the FERRET framework aim to solve in comparison to traditional red teaming methods like rainbow teaming?
The FERRET framework aims to solve the problem of inefficiency and lack of diversity in traditional red teaming methods like rainbow teaming. While rainbow teaming focuses on generating adversarial prompts through a quality diversity approach, it often generates only one mutation per iteration, which can be time-consuming and may not fully explore the range of potential vulnerabilities. In contrast, FERRET enhances this process by generating multiple mutations in each iteration and applying a scoring function to rank these mutations based on their harmfulness and diversity. This results in a significant reduction in the time required to achieve high attack success rates, (OSR), improving the overall effectiveness of adversarial prompt generation. Additionally, FERRET's approach to scoring and filtering ensures that the generated prompts align better with desired feature descriptors, thereby increasing the diversity and quality of the prompts in the archive.
How does the FERRET algorithm work? Please illustrate the entire process step by step, detailing each of the 4 key steps involved in an iteration.
The FERRET algorithm operates through a structured 4-step process in each iteration to generate adversarial prompts for testing LLM vulnerabilities. 1. Sampling. In this initial step, a weak adversarial prompt is selected from the current archive based on its feature descriptor. The effectiveness of this prompt is evaluated using a fitness score, which influences the non-uniform sampling of new feature descriptors for mutation. 2. Mutation. The sampled prompt is then mutated to create multiple candidate prompts. This involves 2 sub-steps. First, aligning the prompt with a new risk category, and second, augmenting it with a specific attack style. A similarity filtering process ensures that the new prompts are sufficiently dissimilar from the original to maintain diversity. 3. Categorical filtering. After generating candidate prompts, this step involves classifying them into risk categories. Prompts that do not align with the desired risk category are discarded, ensuring that the remaining prompts are relevant and diverse. 4. Scoring. Finally, the remaining candidate prompts are evaluated using a scoring function, such as a reward model, to assess their harmfulness. The prompt with the highest score replaces the corresponding prompt in the archive, thereby updating it for the next iteration. This iterative process enhances the quality and diversity of adversarial prompts, ultimately improving the algorithm's effectiveness in identifying vulnerabilities in LLMs.
Can you provide a simple yet illustrative example of how the mutation step within FERRET operates? Walk through the generation of candidate prompts based on a sample prompt and its associated feature descriptors.
In the mutation step of FERRET, a sampled adversarial prompt, denoted as P_IJ, is first selected from the archive based on its feature descriptor, R_I_A_J. For example, if P_IJ is a prompt targeting a specific risk category, say violent crimes, the mutation process begins by generating n new candidate prompts that align with a different risk feature descriptor, R_K_A_L, such as nonviolent crimes. The mutator then performs 2 key mutations. First, it alters the original prompt to align with the new risk category R_K, and second, it incorporates the attack style A_L into these mutated prompts. To ensure diversity, the similarity of the newly generated prompts is assessed using the blue score, filtering out those that are too similar to the parent prompt. This systematic approach allows FERRET to create a diverse set of candidate prompts that target different risk categories and attack styles effectively.
What are the practical advantages of using FERRET over traditional adversarial prompt generation methods, particularly in terms of efficiency, effectiveness, and diversity of generated prompts?
FERRET offers significant practical advantages over traditional adversarial prompt generation methods, particularly in efficiency, effectiveness, and diversity. Firstly, it enhances efficiency by reducing the time needed to achieve high attack success rates, (OSR). For instance, FERRET decreases the time to reach a 75% llama guard to OSR by 45% and a 90% OSR by 15% compared to rainbow teaming. Secondly, in terms of effectiveness, FERRET outperforms rainbow teaming by achieving ASRs of 95% on Llama 2 Chat 7B and 94% on Llama 3 Instruct 8B, which is a 46% and 34% improvement respectively. Lastly, FERRET improves the diversity of generated prompts by employing a quality diversity search approach that generates multiple mutations in each iteration and applies a scoring function to rank these mutations based on harmfulness and diversity, addressing the limitations of traditional methods that often focus on optimizing a single seed prompt.
Can you explain the validation process of FERRET? What datasets, benchmarks, and metrics were used to assess its performance, and how do these compare to baseline methods?
The validation process of FERRET involved extensive experimentation using Llama 2 Chat 7B and Llama 3 Instruct 8B as target models for adversarial prompts. The performance was assessed using two safety classifiers, LlamaGuard 2 and GPT-4, which provided attack success rates (ASR) across various risk categories, such as violent crimes and child sexual exploitation. FERRET's ASR consistently exceeded 94% for both target models, significantly outperforming baseline methods like rainbow teaming, which achieved only 49% ASR without a category filter and 89% with it. Additionally, FERRET utilized a comprehensive dataset to train a reward model that ranked adversarial prompts based on their harmfulness, further enhancing its scoring function. The results demonstrated that all variants of FERRET outperformed the baseline methods, showcasing its effectiveness in generating diverse and harmful adversarial prompts.
Discuss the limitations of the FERRET framework. Are there specific scenarios or conditions where FERRET may not perform effectively, and what might be some underlying reasons?
The FERRET framework, while significantly improving upon previous methods, has limitations that may affect its performance in certain scenarios. One key limitation is its reliance on a large, fine-tuned model to guide the mutations. Without this, the diversity of generated prompts may suffer, potentially leading to less effective adversarial prompts. Additionally, the scoring function's effectiveness can vary depending on the model used. For instance, while the reward model, shows robust performance, it may not generalize well across different evaluation metrics, as indicated by the discrepancies in ASR when compared to LlamaGuard 2 and GPT-4. Furthermore, FERRET's performance may diminish in cases where the initial archive lacks sufficient diversity or quality, as it builds upon existing prompts. Lastly, the framework's efficiency could be hindered in environments where rapid adaptation to new adversarial strategies is required, as the iterative nature of the process may not keep pace with evolving threats.